Okay. Right. I can see a little. I can see a little bit of you off to the right, and I'm. Okay. Yes. I've actually used the Plaskett telescope in Victoria to collect some data for my research when I was up in Canada. I'm a, I'm originally from Newfoundland, so I was a graduate student in St. Mary's University in Halifax, and then I went to York University in Toronto. And so when I was a graduate student, I went to Victoria and collected some data with the telescope there. Yeah, it's kind of neat because both the two largest telescopes in Canada I've used for my research, the Plaskett and the DDO. Right. Yeah. Yes. All right. Yeah. Well, you have to understand the state of knowledge of physics at the time. In the late 1800s, we started understanding that our knowledge of physics related to light and matter was incomplete. And the sun was of particular interest because it's the sun. I mean, throughout history, the sun was literally a god to a lot of cultures. So we didn't actually know how the sun worked at the turn of the 1900. Uh, the obvious thing is it's a big ball of fire, right? Well, when they started making measurements, it couldn't be a ball of fire. The chemical reactions weren't happening. It couldn't be the gravitational collapse and liberating energy that way. And so at the turn of the century, we literally had no idea how the sun worked, where it got its energy. It required Einstein to come along with his equations that equated matter and energy before we finally understood the sun. And of course, anything that affects the sun has the potential to affect Earth in a dramatic way. And so you have this big giant ball of light in the sky, and it turns out we didn't actually know what it was composed of. What we thought it was composed of turned out to be incorrect. And we had no idea where the energy was coming from. So so you have this prototype star 150 million kilometers away, and you had no idea where its energy came from. So it was a huge problem for astronomy to solve. And so this was one of the reasons why it was such a motivating factor. So a lot of, you mean, well, right. Well, the the key was that they needed to understand where the energy was coming from and the composition. They had a pretty good handle about the size of the sun, its temperature, things like this. So the IAU, the International Astronomical Union, has working groups on different things. It's basically to try to motivate efforts towards solving certain problems. And so one of the working groups was related to spectroscopy and astronomy, and solar spectroscopy was really coming into its own at this time. And so this is why it became very related. George Ellery Hale at Mount Wilson had invented the spectroheliograph for looking at the sun and different chemical signatures and mapping the sun. And so we were just really starting to get the tools that we needed. Yes. Okay, well, if you picture a pot of boiling water, the reason why the water boils is because for a fluid, and what we mean by that is a gas or liquid, if the temperature change across the fluid is very high, then it becomes unstable and it bubbles. We call it convection. So the sun's outer layers convect. They have little bubbles, we call them granules, that rise up. So you have hot gas rising from further interior to the sun. They get to the edge of the sun and they radiate energy out into space. They cool off, get more dense, drop back down. However, if you have a magnetic field that's relatively strong, the presence of the strong magnetic field slows the replacement of the hot gas. So it's radiating energy out into space, but it kind of lingers longer than it would otherwise, and so it ends up a little bit cooler than the surrounding layers of the sun, roughly a couple of 100 degrees Kelvin. So now you have a little area that's darker than the rest of the sun because of the magnetic fields, and this is what a sunspot is. The sun goes through a cycle, an 11-year cycle, where you have more and less spots. Where the magnetic fields are concentrated, they can trap charged gas, and this can give off either a solar flare, basically an explosion detonating, or what we call a coronal mass ejection, which is an even larger scale feature that can happen. In fact, we had the aurora borealis last night here in Alabama because there was a coronal mass ejection a few days ago. Yes, right. Well, what's given off is a cloud of charged particles. We call it a plasma. Generally speaking, plasmas interacting with you or your electronic equipment is usually a bad thing. So we have literally billions of dollars invested in space right now. The reason why I can talk to you right now is probably this signal is bouncing off a satellite and being transmitted to you. So this is an electronic piece of equipment, and if you have a solar flare coming along with charged particles, then it has the potential to take out satellites. We have the International Space Station. The astronauts have to watch out for these things. On the ground, you have an electric current that can be created, and this can cause problems. You can have power grids that go out. The famous one about 20 years ago that took out parts of Quebec and the northeastern United States. I was working at David Dunlap Observatory that night, and the power in Toronto went out, and I happened to be scheduled for the telescope. So fortunately, the telescope has a generator, but we saw the aurora borealis from Toronto that night. So it can affect ground communications, satellite communications, and so it's pretty serious stuff. Right. Well, the ultimate goal is to try to be able to predict when these occurrences are going to take place. So liken it to wanting to try to predict earthquakes. the geophysicists are studying earthquakes in as much detail as possible. What happens in an area before an earthquake happens? What happens during the earthquake? What are the effects after? And if we can develop a prediction for earthquakes, then we could potentially save a lot of damage and a lot of lives. The same is true for the sunspots. If we can develop a knowledge of the sunspots and the solar flares and mass ejections so that we can predict them in advance, then we can therefore make things much more safe. Fortunately, we have satellites watching the sun all the time now so that we know when these events are happening. And it usually takes a day or two for the particles to get to the Earth. And so we're at a point now where we have some lead time to get ready for it so we can protect satellites and ground-based things. Well, one thing about Plaskett that I thought was rather special is that when his father passed away, being the oldest son of, I think, 11 kids, he had to basically take over operating the family farm. And people who work on farms at that time, they would be fixing their own equipment. And so he was able to develop his mechanical abilities. And then he became basically a mechanical assistant at the U of T, and then got so interested in astronomy that he pursued it, and the rest is history. So it's quite remarkable. He was a mechanical genius. The 15-inch telescope at Dominion Observatory that he was put in charge of, he had it taking spectra of stars to a higher quality and for shorter exposures than a 100-inch telescope was taking. So he had fine-tuned his observing techniques and his equipment so well that he was outperforming telescopes that were many times bigger than the one that he had. And he's basically the grandfather of Canadian astronomy for all intents and purposes. So really it started with him. The 15-inch telescope at Dominion Observatory was sort of ignored a little bit because they were marking the boundary for Saskatchewan and Manitoba. And so they were all doing surveying, and the telescope really wasn't being used. So he took it over and started doing astronomy. And he made that telescope so productive. They produced, over I think roughly a 5 to 10 year period, the orbits for 15 binary stars, which, if you think about it, this is all hand calculations, measuring things with measuring engines and things, no computers. To do 15 orbits using a small telescope like that is just absolutely remarkable. And then, he went on, he found out about the Mount Wilson telescope, visited there at an IAU meeting, and said, what could we do if we had a telescope that was the biggest in the world? And the Plaskett telescope, for about 3 or 4 months, was the biggest telescope in the world. And until the Hooker telescope came online, the 72-inch. So he really got Canadian astronomy started. And then, and it was a very careful investment. It was like $80,000 or something, right? Which was a lot at the time. But Canadian astronomers continue to sort of do that, where we figure out what our priorities are, and then we make targeted investments. And Canadian astronomy punches way above its weight in terms of productivity and the quality of the research that's being done up in Canada. Okay. 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 I'll be back in a minute.